Hello everyone. I'm BS Anjana, a sixth semester AI/ML student from Global Academy of Technology, Bangalore. Today, I'm going to walk you through a project I've been working on called GrapeCare Robot. It's all about combining AI and robotics to help with grape farming, especially in spotting diseases and spraying fertilizers only when it's needed. It's been a really fun and challenging project that taught me how AI can be useful not just in tech, but also in areas like agriculture. So, why grapes and why a robot? Grapes are one of those crops that easily get affected by disease. If these aren't caught early, they can ruin the whole yield. Now, farmers usually inspect plants manually, which takes a lot of time and isn't always accurate. So, we thought, what if a robot could do this job? It could move around this field, detect diseases on its own, and even spray fertilizer where needed. This would save time, effort, and also improve how crops are managed. Project objective. We had three main goals for this project: monitor grape plants using a camera in real time, detect and identify diseases using AI, spray fertilizer automatically only when it's needed. So basically, the robot should be able to see, think, and act just like a human farmer would, but using AI and sensors. So some of the key features are it can spot diseases in real time using camera and our AI model. It's smart enough to decide when to spray the fertilizer. It doesn't waste any. It can move on its own and avoid obstacles. And it also brings machine learning and robotics together in a single system. Now let's go to the system architecture. First, the camera and sensors collecting data. This includes leaf images and obstacle detection. Then, deep learning model processes the images and checks if there is a disease. Finally, the robot decides what to do: move forward, spray, or send an alert. Some of the components we have used are Node MCU acts as the robot's brain, and then we also have ultrasonic and IR sensors to avoid obstacles and navigate. Then the motor driver to control the robot's movement, and a fertilizer spray that works only when a disease is detected. Now we have dataset and model training. To teach the robot how to identify diseases, we trained it using a dataset of grape leaf images. We used four categories: healthy leaves, black rot, ESCA, and leaf blight. Each category had around 1,700 to 1,900 training images and 400 plus test images. So these are the data sets that we have used. We used VGG16, a pre-trained model, image classification model, and applied transfer learning. We didn't train it from scratch. Instead, we used knowledge VGG16 already had and just fine-tuned it to our dataset. This gave us over 70% accuracy with relatively low training time. This was the phases of our development. We broke the project into five clear phases. The first one was collecting data and researching, which is already done. Training the AI model, this is also done. Building the robot hardware, which is currently in progress. Then putting the hardware and AI together. And then finally testing it on the field. Now let me tell about the working criteria. It keeps moving forward while scanning the plants with the camera. Each image is sent to the AI model, which checks if the leaf is healthy or not. If a disease is found, the robot either sprays the fertilizer, raises an alert, or keeps moving. So it's always in a loop: see, decide, and act. So, what makes it special? What I really like about this project is how it combines so many things. We've got machine learning for disease detection, image processing to prepare the data, hardware design for the robot itself, and even some IoT elements which we can build on later. The future expectations. Looking ahead, we are hoping to improve the accuracy by training on more images, make the robot move better on different types of lands, and also add voice or SMS alerts. So that's the GrapeCare robot, an AI-powered disease detection and fertilization system that bring real change to how farmers manage their crops. Thank you so much for listening so far. Now I'll walk you through the actual code and working demo that I've created. This script is actually for training our deep learning model. Let me walk you through it. The first one is importing the libraries, which is from this step to this step. We improved libraries like TensorFlow, Keras, OpenCV, NumPy, everything we need for building and training the CNN. Then comes extracting the dataset. We extract our leaf dataset from a zip file. If it's already extracted, the code skips it. This keeps the code clean and repeatable. For data augmentation and pre-processing, we use image data generator with rotations, zoom, flips, and more. This helps the model learn better from few images. We also split the data into 80% training and 20% validation. This part of the code is for generating the training and validation data. Then comes model creation with VGG16. We use the VGG16 model but remove the final layers and add our own custom layers with flatten, dense, dropout, and a final output layer of 4 nodes for the 4 diseases. We freeze VGG16's layer so we only train our custom top layers. This is transfer learning. We compile the model using Adam optimizer and categorical entropy loss. We train the model for 10 epochs just to test it quickly, but in practice, we can go for more to improve the accuracy. Then comes saving the model. Finally, we save the training model as plant disease model.h5. This can now be used anywhere, including in real-time webcam prediction. Then we have plant.py. This is the second part of the script. This is where the magic happens. We can load the model and start detecting disease from the webcam. We load the .h5 file and define the class labels black rot, ESCA, healthy, and leaf blight. Open the webcam using OpenCV and create a resizable window to display the output. Now we have predicting it in real time. We resize the image into 224, 224 and then normalize it and then feed it into the model and also get the prediction probabilities. We pick the label with the highest confidence and if it's above 50%, we can display it. Otherwise, it says uncertain. Now we have the sprinkler message. If the disease is black rot, leaf blight or ESCA, we show a red message saying sprinkler is needed here. This stimulates the robot responding to the disease. We use cv2.put text to write the label and message on the frame and show it live. If we press Q, the program quits and closes the webcam. Now let me run this. This is a healthy leaf, as we can see. This is the ASCA affected leaf. It is also giving the prompt as sprinkler is needed here. This is leaf blight. Since this is also a disease, it is telling that sprinkler is needed here. And this is black rot. Now if we press Q, we can exit the screen. So now this is for the disease detection part. I'll also be explaining the robot code. The first step is including the libraries. These are the three libraries that we have included. The AF motor is to drive the DC motors using the Adafruit motor shield library. And then we have the new ping, which is used to work with the ultrasonic distance sensors. Then we have the servo, which controls the angle of the servo motor. This part is for the motor setup. We have four motors here, which is A1, A2, B1, and B2. A1 and A2 are the front, left, and right, and B1 and B2 are the rear, left, and right. Then we have the ultrasonic sensor setup. The trick pin sends the pulse, whereas the echo pin receives it. And then the max distance is the maximum distance that we want to measure, that is 200 centimeter. The servo is mounted on the robot to rotate the ultrasonic sensor left and right so the robot can scan for a clear path when it hits an obstacle. The distance holds the latest measured distance, whereas the obstacle threshold is the minimum safe distance to an obstacle. If the object is closer than 15 centimeter, then the robot will stop and try to avoid it. This starts the serial motor for debugging, sets a low motor speed that is 80 out of 255 for a smooth movement. It attaches the servo and centers it to 90 degree. Now we have the loop logic. This continuously checks the distance. If there is no obstacle, the robot moves forward. If an obstacle is too close, it stops and calls the avoid obstacle. Here we have the get distance function. It waits for 15 milliseconds. This is to stabilize the sensor and then gets the distance from the ultrasonic sensor. If no object is detected, that is 0 centimeter, it sets the distance to maximum, that is 200 centimeter. This part of the code is for the basic movement functions, which includes forward, backward, stopping the motors, turning right, and then turning left, and also avoiding the obstacle. In avoid obstacle function, it backs up a little to create space and then turns the servo to left, checks the distance. It turns the servo to the right and again checks the distance and then it centers the servo. If right is clear, then turn right. If left is clear, then turn left. If both sides are blocked, back up again and then finally go forward. This is how this part of the code works. Let me give you a summary about this. The robot starts moving forward. If it detects an obstacle within 15 centimeter, it stops. Then it backs up, uses the servo to scan both the directions. It picks up the better direction, left or right, and then turns 90-degree and then moves forward. This makes the robot autonomous. It doesn't just stop, it decides how to move around the obstacle. So this is it for the robot code. So that's the complete walkthrough of our GrapeCare robot project. From idea to AI model to real-time prediction. Thanks a lot for watching.